So hello everyone. So welcome to our this week's Efficient AI Seminar talk. Today we are very glad to have the Professor Yingyan from Rice University to give us a talk. Yingyan is assistant professor in the EC department at Rice University. So he leads the efficient and intelligent computing lab at Rice, which focuses on embedded machine learning and aim to develop techniques towards the ubiquitous machine learning powered intelligence and the green AI. So Yingyan received a PhD degree from the UIUC in 2017 and the Best Paper Award at the CIPS, and also the Robert Chain Memory Award for excellent research at UIUC. So she was also selected as a rising star in the EECS by the Stanford University. So she received the NSF Career Award this year, so congratulations to you. So now let's Yingyan to give us the acting talk.
Thank you, Bob, for the invitation and for the kind introduction. And good afternoon, everyone. I'm very glad to have this opportunity to share some of our recent works on efficient algorithm, accelerator, and automated tools towards ubiquitous intelligence and green AI. So I hope this talk to be interactive. So please feel free to stop me if you have any questions and comments. So as we all know that machine learning has been making big news. It seems big news recently. So the community is expecting that it will make a tremendous impact in various aspects of our daily life. Meanwhile, it's well known that there are two driving forces for the recent machine learning breakthrough. One is the amount of big data, and the other is now we have much more powerful computer. So from a computer engineering aspect, these two driving force means huge amount of, when we process the machine learning algorithms, we need to process huge amount of data movement and computational costs. Both will lead to large energy costs. So to provide a concrete idea, next let's look at an example. So we have been, we all have was amazed by Google's AlphaGo, which beat the human champion in the Go game back in 2016. But if we look at the underlying cost, so here I make a side-by-side comparison. So we can see that AlphaGo need over 1,000 CPU and almost 200 GPUs. And in terms of power consumption, commonly cited human brain power consumption is about 20 watts, and AlphaGo need 1 megawatts. So from this example, we can see that powerful machine learning algorithms still need 50,000 times more than human brain. So obviously, this cannot be afforded by most of our daily life device. And the challenge is that this 50,000 times is increasing instead of decreasing, because as we develop machine learning algorithms to solve bigger and more complex problems, the machine learning system is getting more complicated. So that's why looking forward as a community, one grand challenge for us is how we can make a machine learning algorithm not just powerful, but also have better efficiency, energy or time efficiency than humans. For example, in the Go game examples, so instead of having 50,000 times more energy, ideally, if we want to bring machine learning algorithms to most of our daily life device, then it should be 50,000 times less, consumes 50,000 times less energy and power than human brain. So having this goal in mind, so the motivation driving my group's research is we asked the question how we can maintain the powerful performance of machine learning algorithms, but pushing forward improve the efficiency by orders of magnitude. So this is the research problem we are focusing and also interested. So in the past few years, the community, not just from researchers from industry and academia, there have been a lot of work focused on this area, trying to reduce the energy costs of machine learning algorithms but maintain their powerful performance. But still now is open problems. So that's why in my group, we try to tackle this problem from a vertical across stack, from algorithm to architecture, and also develop automatic tool to bridge the two, and also enable efficient navigation over the large joint space between the algorithm and the architectures. And for today's talk, I will sample a few of the recent techniques we have developed. So from the algorithm to the accelerator architecture and automated tools level. So the first one is called early bird ticket. The background behind this work is real-time machine learning has becoming more and more important. By real-time machine learning here, we mean instead of pre-train the model in the powerful computer center or servers, when it deployed to a particular device or application, we need to adapt the model continuously to maintain the performance of the model, because, for example, in the autonomous vehicle case, it's not practical to collect all the data and pre-train the model because the scene that are very kind of various of scene. So a more practical and also useful pipeline is we pre-train the model, have pre-correct data, and then deploy to the device and have it continuous adapt the model parameter to ensure the performance under dynamic environments. This is in terms of healthy care wearables. There are similar motivation. For example, it doesn't make sense to rely on using one model to fit all patients. And even for one patient, as time goes by, the condition, the healthy condition might change, and the model need to adapt the model parameter accordingly. So that's the motivation for continuously learn, adapt the model parameter to ensure the performance in real environments. So this is the background of the few technique I'm going to introduce next. So obviously the challenge is that machine learning algorithm is very costly, and it takes prohibitive cost to train the models. And this contrasts with the constrained resource in most of the daily life device and platform, either have real-time performance, stringent real-time response, for example, in the autonomous vehicle case, or has stringent energy resource constraint. And actually, this real-time machine learning problem also has attracted attention from federal governments. For example, last year, DARPA and NSF launched a program called Real-Time Machine Learning. Professor Yuanbo and I think also other faculty members at Rutgers also have a team is one of the teams selected to work for this program. And I'm fortunate to lead a multi-university team. So that's why in the following talk, most of the techniques we develop are related to real-time machine learning. So basically, we ask the question, can we train or inference a deep neural network to achieve the same or even better performance, but with much reduced energy and time costs? Before we introduce our technique, let's see what's the standard pipeline, meaning commonly used pipeline before our technique. So for training machine learning algorithms and for deriving efficient and compact machine learning model, these figures show the commonly used pipeline. So essentially, basically, we start from dense model and fully train this dense model to obtain the train the model. Once we train the model, we can prune those unimportant connection or weights, and then we continue to retrain it to restore the accuracy loss due to the pruning. And the goal of this pipeline is to derive this compact model, which has much reduced complexity as compared to the dense model, but maintain comparable performance or sometimes even better accuracy. So the limitation and disadvantage of this pipeline is, number one, training this dense network, because it's the most complex one in this whole pipeline, usually costs a lot of time and energy. For example, for standard training, this pipeline for a median model like ResNet 50 or so, this first step will take about 80% of the whole training pipeline from dense model to derive this compact and effective subnetwork. So for this is called lottery ticket. Essentially, it say the lottery subnetwork that within this dense network that can achieve similar or even better performance as the dense one. So this was called a lottery ticket by one of the ICLR 2019 paper. So for today's talk, the technique we develop improve on point based on this pipeline. So the first technique I'm going to introduce is saying, in this whole pipeline, you don't need to go through this time and energy consuming process. You can just partially train the dense network, and we will be using our technique, we will be able to draw the early bird ticket around 10% of the training this dense network, instead of going through fully train this dense model and then go through the prune and retrained iterations. And then that's the first technique. Basically, we reduce this whole pipeline to a small step that partially train the model to draw the lottery ticket. So that's why we call it early bird ticket. And then the other two techniques from the algorithm level, we try to say, after we derive this lottery ticket, to train it to train this lottery ticket still can be very complex. So we further develop technique to improve the training efficiency of training this lottery ticket, meaning the compact and effective subnetwork. And one highlight of our technique is we not just improve the training efficiency. Using our technique, after we train the model, naturally the inference often become more efficient. And we also further develop technique to reduce the inference cost. So let's see the first one for the next few minutes. So as we mentioned, the first the pipeline on top is the progressive pruning and training pipeline. That was a standard training pipeline to derive compact and effective subnetwork. And then this early bird train technique we developed was published in iClear as a spotlight paper. The idea is very simple. So looking into this pipeline on the top, we know that the whole pipeline essentially want to find the important connection or important subnetwork within this dense network. Then we hypothesize that it does not necessary to train the dense network fully up to convergence, because it doesn't matter whether how well this dense network will perform. The key is to identify subnetwork that within this dense network that can have comparable performance as this dense network. So that's hypothesis motivate our early bird train network. We have 3 contributions in this first paper. So first, we are the first to identify and discover that such important dense network emerge at the very early training stage. For example, let's say the total training time as 100% when we fully train the dense network. So we found consistently that around 10% that we can this sub-important network emerge. And then by doing so, after we discover this phenomenon, meaning the existence of such early bird ticket, we develop a low-cost detector to automatically detect it, meaning using our detector during the training process of the dense network, it can automatically identify and inform us that early bird ticket has emerged. And by doing so, we can reduce this whole pipeline to a much shorter pipeline, which can largely reduce the training cost, time and energy. So this is a high-level view. Next, I'm going to briefly go into each of the bullets to elaborate what I really mean here. So the first contribution is we discovered that the early bird ticket exists. So as we mentioned, lottery ticket means some network within the dense network that can perform similar or even better as compared to the dense network. So we find that we define the subnetwork to be some network that join at the early training stage as compared to this one fully trained. Join at the early training stage, but is also effective and compact subnetwork, meaning achieve comparable accuracy as compared to the dense network. So this is what we mean by early bird ticket. Essentially, it's saying we draw this lottery ticket much sooner during the training stage. The first contribution, we find that early bird ticket exists through across different model and data set. Here I show 2 examples here. So lottery ticket means we fully trained the dense network and iteratively train, approve, and retrain to get this lottery ticket. So let's say this denote the lottery ticket, the accuracy. The y-axis is the accuracy. The x-axis is showing that for these 2 examples, the training takes 150 epochs. So it shows the achieved accuracy of the subnetwork drawn during different stages of the training process. For example, fully trained dense network, fully trained require 160. This is the accuracy achieved by the lottery ticket. And we can see that the lottery ticket drawn earlier, meaning earlier during the training process, is effective as because it achieves better or comparable accuracy as the lottery ticket. So we observe this observation consistently across different model and data sets. So that's how we claim the existence of early bird tickets. And the next one is we develop a low-cost detector to automatically detect the emergence of such early bird ticket, because during the training process, once these early bird tickets emerge, then we can stop the process of training the dense network. So that's why it's important to have a mechanism to automatically detect the emergence of the early bird ticket. So here, I briefly show our detector design. It's very simple. So basically, during the training process, each epoch, we use a matrix to store the connection of the subnetwork during the prune and training process. For example, if a connection is maintained, we use 1. If it's pruned, then we use 0. And then we essentially compute the Hamming distance between the matrix between conjective epoch, for example, t and t plus 1. So if this distance is small enough, then we claim that early bird ticket exists. The hypothesis is that the subnetwork or lottery tickets within the dense network, they should be similar. So once it emerges, it shouldn't change a lot. So that's the motivation. And here I show the bottom right figure show a visualization. So this is the number of epochs. And in this example, again, the total training process take 160 time epochs. So we can see that clearly the distance small, very small means it already emerged. This shows that around the 14th epoch, the early bird ticket already emerged. And the advantage of this detector is very simple, meaning the overhead is very small, but it's effective. The third one, naturally, once we know such early bird ticket emerge at the very early training stage, so that means we don't need to train this dense network fully to draw the lottery ticket. This can save large amount of time and energy costs for this to train and derive this compact and effective subnetwork. So this is the third contribution. By leveraging the existence of such early bird ticket and using our proposed early bird detector, so we can largely reduce the time and energy costs of this progressive prune and training pipeline to a much shorter pipeline. And because training this dense network dominate the time and energy costs of this whole pipeline. So that's why such early bird training can largely reduce the time and energy of this training pipeline. For the interest of time, I only use one slide to summarize our main results. So we validate across different models and data sets. And the metric we consider is accuracy and the total energy, training energy cost. And for the energy, we measure using NVIDIA Edge GPU. And the baseline we consider were 5 state-of-art efficient training technique back in that 2019. And this bullet summarized. So as I showed earlier in the pipeline, it can largely reduce the energy cost from over 5 times to over 10 times. So next, I'm going to show one of the interesting visualization. So we have seen so far that early bird tickets exist in the very early training stage, this figure kind of visualizes the decision boundary. Essentially, the neural network trying to draw some decision boundary in the input data space. So this visualizes the decision boundary, the network of the network from during the whole training process from epoch 1 to epoch 160. So we can see that at the early epoch, the boundary changed a lot. But later, after around 10 epochs or even fewer epochs, the decision boundary kind of similar. That kind of also validate that indeed this subnetwork emerged at the very early training stage because the decision boundary largely maintained to be the same. That means the subnetwork, the effective and compact subnetwork already emerged at the very early training stage. Another interesting connection is I found in one of the Nature paper back in 1982, it showed that in our human visual system, there are a similar early critical early stage. So earlier we we have seen that the early bird ticket exists and actually also important because we found that the accuracy achieved by the early bird ticket even outperformed that of the lottery ticket. That means it's important to draw such winning ticket at the early training stage. And this Nature paper showed that our human visual system have such a critical early stage. For example, for kids, in particular for kids that if they are able to be exposed to visual environment, then their visual system can be well developed. But in some case, or unfortunate case, kids who were born without this capability, then later, even if they can be exposed to visual environment around, their visual system cannot be well developed. So I personally find this connection kind of interesting and inspiring. So this kind of summarizes the first technique I would like to introduce today. So for the next few techniques, I will briefly mention what's the problem we try to solve and what's the key idea and how is the results, meaning whether it's effective as compared to state-of-art technique. So the next one is called flat train or cyclic train. So it's published in New Reefs 2020 or iClear this year. So earlier we have shown that we can largely reduce the training pipeline by drawing early bird ticket. But as I mentioned earlier, training the lottery ticket, meaning after we draw the subnetwork, to train this subnetwork for deployment still very costly. So in the next few algorithmic technique, we try to say whether we can further improve the training and inference costs of those lottery tickets. So one of the motivating observation is recent Dnn training optimization works has shown that during the training stage, Dnn learns different patterns during different training stage. For example, one of the papers showed that at the early stage, Dnn tend to learn low frequency features that are more robust to perturbation or noise, but it's not as accurate. And at the later training stage, Dnn optimization tend to learn the high frequency and more accurate feature. So this observation kind of motivate us to ask the question that Okay, if the training stage, different training stage have different roles, that means the training cost should be adapted accordingly, meaning at the early and medium and later training stage, the model are learning different features. That means the accuracy and capacity of the model should adapt accordingly. So this is the motivation observation one. The second observation is often when we do efficient machine learning, efficient training and efficient inference technique are decoupled. So we hope to target technique that improve not just the training efficiency. Once it trained using our technique, the inference efficiency can also be largely reduced. So we target a unified goal of both efficient training and efficient inference. And the first technique is called break train. The idea is very simple. As we mentioned, different training stage has different role. And we kind of hypothesis at the early training stage, the accuracy requirement on the model is smaller because having larger noise can help the model to better explore the design space. And then later, once the model converges to a good local minimum, then we need a higher accuracy. So in this talk, we will use this to represent the Dnn training process, this circle. So the break train technique is to temporarily and spatially squeeze out the bit precision, unnecessary bit width within the model. The first technique is to progressively, meaning instead of using static precision, for example, 8-bit, we start from 3-bit and progressively increase it up to 8-bit. And that's temporarily squeeze out the unnecessary bit width. And the second technique is to dynamically squeeze out the unnecessary bits because different training samples have different complexity and correlated with different layers. So for each input, we fractionally adapt the bit width of each layer to this particular input. So that's how we spatially squeeze out unnecessary bit widths. So by combining these two techniques, this figure shows that our techniques converge much faster. This is the accuracy versus the number of max, and also achieve even better accuracy. For example, in this case, ResNet 70 on CFA 10, the accuracy is slightly improved, and the reduction in terms of max, the number of max can be reduced over 70%. And we also show the energy and latency reduction. And having that similar motivation, another technique that we developed, published in iClear this year as a spotlight paper is called cyclic precision training. The motivation is the same. So recent Dnn optimization, as we mentioned earlier, show that different training stages have different roles. So we hypothesized that dynamically schedule the precision can improve the efficiency because it reduces the average precision. At the same time, might help the model to explore because the dynamic precision introduce noise. So this is the idea. Instead of using fixed point precision during the training process, we cyclically schedule the precision, for example, between 3 and 8. We cyclically change this precision. And the good surprise is that we find that not just using such cyclic precision not just reduce the average precision, but also help the model to converge to better local minimum. So this we use a state-of-art loss landscape tool to visualize the converge minimum. So wider here and the distance between different circles here means better minimum. So as compared to static and progressive, cyclic achieve the best local minimum across different model and data sets. And also, we find that using cyclic precision reduce the accuracy variance. For example, this is the variation of the test accuracy on 10 training runs, meaning we repeat the same training process by 10 times. The red one is trained using cyclic precision. We can see that the variation is largely reduced. So that's another a nice surprise. More interesting and exciting is we find the cyclic precision even outperform the full precision model. For example, in this example, we trained the ResNet 18 and 34 on ImageNet. Compare with the full precision 32-bit, the cyclic precision training between using precision range between 8 and 32 improve the accuracy by almost 1%. In ImageNet, this is a non-trivial improvement. So, so this kind of summarize the performance for the cyclic precision training. And the last algorithm level technique I would like to mention is the ship at the net. So like I mentioned earlier, so we have used early bird ticket to reduce this pipeline. And then once we derive the pipeline, once we derive the lottery ticket, we use flat train and cyclic precision to reduce the training cost. And this ZipNet is saying on top of that, we know that multiplication can be represented or implemented using bitwise ship and add. So we replace all the replace all the ship and add all the convolution layer using ship and add layer. The motivation is ship and add in hardware is much more efficient than multiplication. So this is also a simple and effective technique to derive a ship and add net version of state-of-art Dnn technique, maintain the performance but largely reduce the hardware cost. So this kind of summarizes the algorithm level technique we have mentioned. And in the remaining a few minutes, let me briefly mention two accelerator level techniques we have developed recently. So for the energy cost of machine learning algorithm, the previous technique I have mentioned kind of show that in the algorithm level, there are different redundancy opportunity we can reduce to improve, to reduce the model complexity. But then when we execute those models to hardware, there are still opportunity we can further reduce the energy cost and improve the efficiency. So this slide kind of show that each generation of algorithm also motivate innovation in the architecture level. Now it's a data-centric, so machine learning algorithm has massive data. So how to develop data-centric, optimal data-centric architecture, that has been many works. But now still is an open problem. So what is the optimal solution? For the first technique we developed is called, the first technique I would like to share is called Smart Exchange. So the concept is very simple. I will so this figure show the motivation. So in how well access DRAM as compared to the corresponding computation, there are 200 times energy gap. So this motivates us to ask the question, can we trade higher cost memory for lower cost computation? Meaning, because DRAM is much more expensive, 2 orders higher, can we do more computation and to reduce the amount of DRAM access? So for that, the smart exchange had a very simple concept. So the simple analogy about this technique is saying, assume we have 1,000 data we want to access from DRAM. Now, instead of access all the 1,000 data from DRAM, which has much higher cost, we decompose this 1,000 data to find some structure in this data. For example, in the paper, we do rank decomposition. We stack all the data to a syntol matrix and then do rank decomposition. Now, instead of access and store the 1,000 data, we now only store 10 data and access 10 from the DRAM. And the remaining one, we use computation because once we know the basics and the coefficient, we can restore all the remaining 990. So that's the concept. And then we design a dedicated accelerator to leverage this algorithm level concept. So this slide kind of summarize the results. So compare with multiple state-of-art accelerator, this smart exchange algorithm accelerator code design consistently improve the efficiency and latency. And also one highlight of this work is it is the first framework that integrates 3 mainstream compression techniques, decomposition, the rank decomposition, and we further use pruning and quantization to reduce the computation, the actual computation cost that is result to reduce the DRAM access. And for the interest of time, maybe I can skip the second accelerator technique and go to the last one. So far, I have shared some of the technique we developed in the algorithm level and the accelerator level. I'm excited to share this last branch, automated tour, because I think it has gained more and more importance. So far in the community and in my group, we have important learning through the process of develop efficient machine learning techniques. So we found that hardware efficiency is critical for enable more extensive application for powerful machine learning algorithm. And then to maximize the efficiency, we need to consider both algorithm and hardware. But the reality is the development of machine learning algorithm is much faster than that of the hardware development. So this gap kind of motivate us to develop automated tool to bridge the gap, because essentially we have machine learning algorithm innovation almost on a daily basis. Hardware development needs months or even years. So if we have automated tools, then we can expedite the development process. For that, let's look at the challenge of developing DNN hardware. Number one, the design space is large. The algorithms have different kind of structure. For example, CNN have some pipeline and transformer have another kind of pipeline, and RNN. Different DNN model have different pipeline and layer structure. And when we map the algorithm to be executed in the hardware, there are many ways to do so. Different way can have large performance gap. For example, one of the NVIDIA paper showed that the different mapping can lead to over 2 orders of magnitude of performance difference. And there are also large design space in the hardware side. So there are many hardware IP choice. For example, to implement convolution, there are many different IP we can use. And within the accelerator, there are different memory hierarchy and P-array size. There are how big is those memory, how many hierarchy we use, what is the shape and size of the processing array. So there are basically large design space, and this needs a cross-discipline knowledge. That kind of explain why the hardware machine learning accelerator development is much slower than that of machine learning algorithm. So in this work, we asked the question, can we largely automate the process of DNN chip design? By auto DNN chip, we mean how we map the algorithm to be a temporary spatially scheduled in the hardware. And in the hardware, and how we develop the memory hierarchy, for example, how many memory hierarchy, how big is each memory hierarchy, and the P-array size and shape, and how the P-array talk to different memory hierarchy. So this is a high-level goal. The input is the target, the hardware stack, and also the machine learning algorithms. And we have a chip predictor, which can predict the performance, and also chip builder to explore the large design space to automatically identify the optimal mapping and accelerator, and then automatically generate the RTL code. And for the interest of time, I only show one result here. It's a very encouraging result. The y-axis here show the energy per image during inference, and the y-axis is the required latency. So the visualization here show that among the million choice of design, how the two-stage design space exploration, DSE, rule out the unimportant design. For example, after the first stage, we only have tens of choice, and after the second stage, we have this optimal design. The encouraging result is by using this auto DNN chip, which takes about a few hours to search the optimal design. This is the performance outperform human expert and award-winning design. And that kind of cover all I would like to share today, the algorithm architecture and automated tool level technique. And finally, I would like to take this opportunity to thank my students and my collaborators at RISE and outside of RISE, and generous sponsors from different agents. Thank you all for your attention. Any questions? I would love to hear and discuss.
So thanks, Yingyan. Thanks for your very excellent talk. So if you have, if the audience have any questions, you can input the questions in the chat or on the Q&A text box. So I think I can pick the question. So you once worked like in the low bit precision training and also like the early bird ticket. So in your opinion, so how do you view the pros and the cons of the different types of the efficient method, the computation and the specification and so on. So how do you view their, especially in the context of training, how do you view their potential there? Because we also know there's a lot of the sparse training papers come out recently.
Yes. Yeah. Yes. So I think if correct me if I'm wrong. Your first question basically saying the potential, my comment on the potential of early bird ticket and the dynamic precision training. And then also the dynamic precision. The second question is the potential of the dynamic of quantization as compared to different pruning technique. Is that correct?
Yes.
Thank you. So for the first one, I think they are orthogonal because like I show in this slide, so we first want to draw draw the compact and effective network, some network that is often called lottery ticket within this dense network. So this essentially is to identify the connection, the important connection. So this can be drawn at a very early training stage, and later that we can use different efficient training technique to fully train this lottery ticket to before the deployment. So that's the first relationship. Basically, they are orthogonal, can be applied on top of each other to reduce the performance. And then for quantization and pruning, I think they are both promising and also orthogonal. But when it comes to the training cost, I think quantization can potentially squeeze out more saving because when it comes to the granularity, the bit width bit is the smallest, the finest granularity we can consider. So that's my personal view. And this dynamic precision training actually is a surprise, a nice surprise. We originally, as I show in this slide, originally the motivation is saying if different training costs has different role, that means we shouldn't fix the training cost during the process. For example, for the stage that need a more accurate feature extraction and update, we should allocate higher precision. For the stage that the model try to explore where is a good local minimum, then we don't need a very high accurate update. That means we can use lower precision. That's the original motivation. We want to improve the training efficiency. But I think personally, I think it's intriguing to find that doing so even largely improve the robustness and also the even outperform the fixed point 32-bit. So that's a nice surprise I recently observed. Yeah. So hopefully I answer your question. Basically, I think they are mostly orthogonal, but a big quantization when it comes to squeeze out the training cost is has the greatest potential due to its finest granularity.
Okay, thank you. Yeah, so actually, recently I'm thinking about one question. So since we have several different type of the compression approaches, they can be either used in the inference or using the training. So as you just mentioned, they can be complementary, work together. So now let's think about one scenario. For example, using the pruning, we can achieve like 5 times compression or 5 times efficiency increase. Using the quantization, we can achieve another 5 times. So put them together, so we can achieve 25 times. So,
yes.
But on the other side, so if we just purely using the pruning or using the quantization with the 25 times, in that case, we may suffer very severe average drop. So why does this phenomenon happen? I'm very curious about this kind of phenomenon here.
I see. I think maybe I can share my 2 cents here. So I think you provide, you actually bring up an excellent point. So what we do from the join early ticket and then further to quantize is like what you mentioned. So by pruning, meaning remove those unimportant connections, we can reduce 5 to 10 times, and quantization we can have another and combine. I think the reason we combine by combining this can have larger potential to reduce the complexity is because they are working in different granularity. For example, the network, the pruning handle more in the network level, meaning which connection are important and which are not. It's like a yes or no question. And quantization is saying how important this, instead of saying just using hard decision to say yes or no. Quantization, we can view it as a fractional decision to determine the importance of the connection and the weights. So that's my personal view. So that's why combining these two, because without the pruning, you actually allocate, maintain those unimportant connections that have redundancy and cause unnecessary time and energy. But by using quantization, you can more accurately identify the importance of the network. But I think it's an intriguing question also. For example, I once also asked such a question. We are trying to answer pruning and quantization, they kind of orthogonal. Which come first? Would that have a large impact in the performance and why?
Yeah, I think currently the pruning is kind of still more popular, right? The specification is more popular. As compared to, because quantization, we know that so every hardware we will definitely use the quantization. And also, in your opinion, so we know that right now, recently the IBM reports that they have already achieved like tremendous 4-bit quantization training, right?
Yes, they
So
have
do you
a
believe
special.
that? Yeah, do you believe that we can have like the 1-bit or 2-bit training in the future?
I think so. Depends because the reason is as follow. Number one, for 1-bit and 2-bit, there are already work use application use 1-bit and 2-bit that for the application where the energy and the cost are more stringent. They do so to compromise the accuracy. So that's one, meaning some of the applications when energy is more of a concern, that or meanwhile they can tolerate the accuracy job that BNN or 2-bit would have large refined great applications. Number two, actually this related to your previous question. I still think we can use lower bit but have more connection. So this can be another way to, for example, if we use wider network, although it's BNN, then hopefully we can maintain the accuracy, meaning the accuracy job will be minimal. Actually, recent accuracy improvement in the field of BNN is very promising. I think since the emerge of BNN, the accuracy job started from 20%, now is only a few percent. So I kind of promise, I kind of optimistic in this direction.
Okay, so then, sorry, I have another follow-up question. So because recently I also read some of the posts from some researchers in the Google, and they said that so when we narrow down for our application in those like the smartphones, so that already use the current like the INT8 processors to support that, they claim that so the 8 bits is already good enough because the commercial processors, so they always use the 8-bit. So if we pursue the 4-bit or 2-bit, this kind of due to the current compiler issue or something else that so even use the 8-bit or the 2-bit, the 4-bit and the 2-bit, unless you customize your own chip. So then if you run the low bit model on the current off-the-shelf devices, so the performance improvement will be not so significant as we expect. So how do you think about this claim?
Yeah, I think number one, it's true that because most of the hardware supporting tools, for example, compilers and the existing hardware infrastructure in most of the industry setting support the 8-bit or even more bits. So that's why the potential of lower bit low precision network have not yet been fully unleashed. But then this is the current situation. But I believe still, for example, like you mentioned, IBM has showed and spent a lot of investment to push forward this direction. So basically, in the near future, I believe there will be more supporting compilers. For example, I recently also reviewed quite a few papers. There are compilers and hardware accelerator design to dedicate for those low precision network. So basically, my answer is current situation is true, like you mentioned. Due to the lack of support, the potential of lower precision DNN has not been unleashed or fully unleashed. But as it's one of the most promising direction to reduce the energy and the training and inference costs. We have observed that the industry are following up, the community are following up to develop supporting tools for those low precision models. So I believe in the near future, that potential will be become reality. I think there are a question in the chat. So I see a question say hardware software are required. Does it mean that we need to develop those software hardware for both training and for example on large GPU and mobile? I think if I understand correctly, this question is to follow Professor Yuanbo's question on the potential of low precision training. My answer is not really true because number one, there has been compiler work trying to see how we can develop compiler to compile the low precision model to be executed in general computing platform, for example, GPU, CPU to improve the performance. But when it comes to hardware, there are also two trends. One is to using the existing hardware infrastructure or hardware platform in mobile settings and try to optimize the compilers to improve the efficiency. The other direction is like you mentioned, yes, if we can have dedicated both dedicated hardware and software, then the benefit of low precisions in the actual deployment will be maximized. So basically, yes, we can either use software level technique in general computing platform to unleash the benefits of such low precision model. But to maximize the benefit, we indeed need a both dedicated algorithm and hardware.
Thank you. And I think I just want to add one point. So to respond to to you. So I think another maybe potential promise field for the low precision is for the ping, right? So you have one ISCA paper on you don't have time to introduce that. I think for the processing memory, so low bit is kind of the mandatory due to the limitation of the actual device. And I think in that case, so the low precision inference or training that like your work can play a very important role there in that field.
Yeah, actually, that's very true. Like you mentioned, the memory cell, the physical limit make it very challenging to develop high precision memory cell. And also the ADC, DAC, which often dominate. So if we can have support low precision, that actually also can largely improve the efficiency and the performance.
Yeah, I think that is also what your RTML right now, your RTL existing RTL project try to target, right?
Yes. So Boris focused more in the pin the analog and mixed signal level. So we recently tried to collaborate to see how we can supply him with corresponding network. Yeah.
Yeah. I look forward to those works. Yeah.
Yeah. Also, we will see very soon. I think it's next month. Yeah.
Okay. So, any other questions? So, if no, so this is the end of today's talk. So again, thank you, Yingyan. Thank you so much for your
Thank you.
give us this very excellent talk. Okay. So
Thank you, Paul, and thank you all. And I enjoyed the discussion. Those are very insightful questions.
Yeah, me too. Okay. Thank you. Have a wonderful day.
Bye.
Bye.